Okay, so today I plan to finish unit 2 of your syllabus. From tomorrow onwards, we'll start unit 3. But your continuous assessment test will only be for unit 1 and unit 2. So I hope everyone knows the question pattern for your continuous assessment test. You are supposed to have just a minute. You're supposed to have 15 MCQ and 15 MCQs. And if I remember correctly, out of that 15 MCQs, you have to answer 15 MCQs and 5 short answers you will have. You have to answer 15 MCQ and 3 short answer out of your 5 MCQs. Out of the 5 MCQs, you have to answer 3 short answer. So the total marks will be 24 marks for your CAT 1. Okay, so let us begin from this tunnel diode. I will quickly cover tunnel diodes and Schottky diode, and then with that we will finish the unit 2 syllabus. So what is a tunnel diode? Tunnel diode, like other special diodes that we discussed, like the Zener diode and what is that, LED photodiodes and all we have discussed. So it's also another special type of diode. Okay, it's another special kind of diode. And here, what is so special about this tunnel diode is that in this tunnel diode, you can actually have what is called quantum mechanical tunneling. Quantum mechanical tunneling. So I don't know if you have heard of this quantum mechanical tunneling. So quantum mechanical tunneling is that, you know, that in classical system, suppose you are traveling with a vehicle like this, and if your vehicle engine cannot give enough energy, can give enough energy, it can climb this, right? But if the maximum power given by this vehicle engine is less than the energy required to climb over this kind of steep. Okay, so if this vehicle engine cannot give maximum power which is sufficient to overcome or to climb over this kind of steep, then this vehicle can never cross this. That is in a classical system. Like in the case of, suppose you have a certain wall and you are throwing a ball on the wall. If the kinetic energy of this ball is insufficient to penetrate through this wall, this ball will never penetrate through it. But if you have a certain soft surface, like spongy surface and all, if you fire a bullet, if the kinetic energy of this bullet is, say, when you are firing bullet, means this lead ball which is coming out of your muzzle, your gun muzzle, it will travel with a very high kinetic energy. So when it travels with a very high kinetic energy, it can easily penetrate through many of the surfaces, right? It can easily penetrate through many of the surfaces, like wooden surface also it can penetrate through, plastic surface also it can penetrate through, isn't it? So like that, if the kinetic energy of this classical particle is greater than the energy required to pass through this kind of barrier, it will easily pass through. But if the kinetic energy of this classical particle is less than the energy required to pass through such kind of barrier, like throwing a ball, it will never penetrate through this, right? So that is in a classical system. But when it comes to a quantum mechanical system, if I have a quantum particle like electron, as you know, it has a dimension which is comparable with Planck's constant. So if a dimension of the this electron is like somewhat comparable with quantum realm, that is the Planck's constant, then the particle will not behave like a classical particle. It will behave like a, what is called a quantum particle. So a quantum particle does not behave like a solid particle. When a quantum particle like electron travels, such motion of quantum system, it will be associated with what is called wave function. Such motion of quantum system will be associated with wave function, and we cannot write Newton's second law, force equal to rate of change of momentum, for such kind of particle. For writing the equation of motion in every classical system, we can use Newton's law, which says that the force acting on any classical object is equal to rate of change of momentum of that particle. But that Newton's law is no longer valid when you get into microscopic system, when the dimension is so small that it is comparable with what is called your Planck's constant, and then that particle, when it starts behaving like quantum system, it will not behave like a particle, it will behave like a wave. So there will be a wave function associated with it. So instead of writing the particle equation of motion using this Newton's law, you have to write the equation for this wave function. The equation for this wave function is what you know it as a Schrodinger wave equation. Okay, Schrodinger wave equation is equivalent of equation of motion as in the case of this Newton system. In quantum system, we this Newton law, the second law of equation, the second law of Newton is no longer valid. So we write equation of motion. When we solve the equation of motion in terms of this Schrodinger wave equation, it is predicted from quantum mechanics that quantum particle like electrons and all, if the barrier width is quite thin, and the barrier has a finite height. If the barrier has a finite height and the width is quite thin, this quantum particle, even without having enough energy to climb over this barrier, it can quantum mechanically penetrate through this barrier. Unlike the classical system, or the classical system will penetrate through the barrier only if it has a kinetic energy greater than the barrier energy. For those classical system having kinetic energy less than the barrier energy, it can never penetrate. But in a quantum system, even if the energy is less than the barrier height here, because once you express the equation of motion of a quantum system in terms of your wave function or your Schrodinger wave equation, when you solve this kind of quantum mechanical problem in 6th semester, you will study quantum mechanics, you will find that quantum mechanical tunneling actually can occur, and this quantum particle can pass through the barrier even if it does not have any sufficient energy to overcome it. So that is the same thing that will happen here. So eternal diode is a special diode in the sense that this is also called degenerate semiconductors. Degenerate diodes or degenerate semiconductors, it is made up of degenerate semiconductors. Degenerate semiconductors is when the doping density is extremely high. Doping density is extremely high, and the barrier width or depletion width is very, very thin. Okay, when the doping density is very high, the depletion width is very thin. The p-n junction thus formed is made up, we call it as made up of degenerate semiconductors. Doping density is very high means in the case of n-type, the doping density is nd, number of density of donor atoms. In the case of p-type, the doping density is number density of acceptor atoms. So when these quantities are very high, you have high concentration of free electrons in n-type, very high concentration of holes in p-type. So when we form a p-n junction with such degenerate semiconductors, the depletion width is now very thin. Okay, this depletion width is now very thin. So now when you have such semiconductors, if you don't give any biasing here, no current can pass through it. Here in the n side, you have free electrons in the conduction band. In the p side, you have holes in the valence band. So in order for the electrons to pass from this n side to the p side, unless you give energy, it cannot pass through, right? Now, when you give a small forward potential under small forward voltage, when you give a small forward voltage, what happens is that, uh, see, in normal p-n junction diode, suppose this is the IV characteristic curve of a normal p-n junction diode. So unless and until you give sufficient energy, let's say 0.7 volt or something, to climb over the potential barrier, unless and until you give such amount of potential external forward voltage, you cannot have any current in the forward direction, right? This is the usual IV characteristics of a normal diode. But what happened in this semiconductor p-n junction made up of degenerate semiconductor is that when you start giving a small forward voltage, like for example, as you see, the current immediately starts. So when your forward voltage is slightly above 0 volt, even if it is less than the knee voltage of the, if it is less than the knee voltage of the usual p-n junction diode, even if it is at much a lower voltage than the knee voltage of a usual p-n junction diode, in this tunnel diode, you will have a current just immediately above 0 voltage. Okay, so what current is that? That is actually the current due to tunneling of electrons. How does tunneling occur? So you know that in order to have the usual IV characteristics, when you supply negative potential or negative energy to the free electrons here, the energy supplied from the external forward voltage has to be sufficient to climb over this potential barrier and jump to the P side here. But in this tunnel diode, before that knee voltage is overcome or the potential barrier is overcome, the as you slightly increase the forward voltage, the electrons from this p-n junction, the n-type of the p-n junction, can penetrate through the potential barrier without overcoming the potential barrier. The electrons, even if they have less energy than the barrier potential energy, when the barrier width, the depletion width, that is the barrier width, is very thin, then electrons can easily penetrate through the depletion width, the potential barrier there, the p-n junction. Okay, so the process is called quantum mechanical tunneling. So interestingly, as you increase the forward voltage, you are aligning this electron on the n side with the holes on the p side, and you are getting more and more electrons tunneling across the barrier without overcoming the potential barrier, and therefore the current increases like this. The current will increase immediately after just above 0 volt, and the current will attain at a certain point the maximum tunneling current. The maximum tunneling current will attain. Now, when you increase the forward voltage further in this direction, you will find that you are lifting this conduction band from the n side further up, and you are lowering the valence band on the p side further down. And when that happens, the electrons which are on the conduction band will misalign, will no longer be aligned, will become misaligned. This because the electrons are lifted up here. The electrons in the conduction band of n-type are lifted up here. So when such misalignment occurs, the number of free electrons from the inside which tunnels across the p-n junction will decrease, and then eventually you have this region, that is tunneling current will decrease, right? Tunneling current will decrease. Now, as you continue further, after attaining the minimum tunneling current, when your forward voltage is able to overcome potential barrier, when the forward voltage value is such that the electron in the conduction band is lifted up, the electron energy in the conduction band of n-type is lifted up. So these electrons will now have sufficient energy to overcome this potential barrier easily as you continue increasing the forward voltage. So at that point, that is where above the knee voltage, a current will start increasing again, because these electrons is able to overcome the potential barrier now because of the sufficiently large forward voltage, and you will have the usual IV characteristic curves for PN junction. So here beyond this point, no more tunneling, no more tunneling. So the current which is rising up beyond this point is due to the forward voltage, which gives sufficient energy to the electrons in the inside to overcome the barrier. And as you increase the voltage further, the current will rise further and it will increase exponentially like the usual PN junction diode, something like this, above the new voltage, right? But what happened in the tunnel diode is even below this new voltage, just above this, you have a tunneling current. And then as you increase the forward voltage further, the forward voltage is increasing in this direction. As you increase the forward voltage further, the misalignment of the conduction band and the valence band of this P type and will occur, and then the tunneling current will decrease. And then beyond this new voltage, when you are giving sufficient forward voltage to overcome the potential barrier, the current will start rising again. So this is the tunnel diode IV characteristics. This is the usual normal PN junction diode. So that is the difference here. Okay. So quantum mechanical tunneling actually helps in having current even at a very, very low forward voltage. Under normal circumstances, we would not have any electrons from the N side crossing over to the P side unless there is a tunneling. So the tunneling occurs when the depletion width is very thin, right? So to make the depletion width very thin, we make the doping in the N side and doping in the P side extremely high, so that N side is a degenerate N-type semiconductor, P side is also a degenerate P-type semiconductor. So only when we have a degenerate semiconductors forming PN junction, you will only get a quantum mechanical tunneling. And those kind of like special diodes in which you can have a quantum mechanical tunneling is called tunnel diode. In normal PN junction diode, this tunneling, quantum mechanical tunneling, cannot occur. So the usual IV characteristics of a normal diode is like this only. But in this tunnel diode, the IV characteristics is now change. So you have what is called a region of negative resistance. Negative resistance in the sense that as you increase the voltage, that is here, suppose this is the initial value of voltage, this is the final value of voltage. So voltage is increased from this to this. So the del V is when you have a del V positive, that is increasing voltage, the current is what? The initial value of current is here. Corresponding to this point, the current value is here. So current value is decreasing here. So del I is negative. So the resistance V equal to IR. So resistance R is equal to del V upon del I. So if you have a del V positive between these 2 points, that is voltage is increasing from this to this, then del V is positive. Corresponding to increase in voltage, you have a decrease in current from this to this. So del I is decreased. Therefore, you will get a negative quantity. Yeah, del V is positive, del I is negative, means the ratio of positive quantity and negative quantity is negative. So you will have a negative resistance in this region. So that is a very interesting phenomena which only occurs in this kind of tunnel diodes. Go on. Okay. So the circuit symbol for tunnel diode is this. It is slight modification of this normal PN junction diode just by putting this thing here. And this, wherever you are having this shows that this is a tunnel diode. And so you know that in this tunnel diode, you can have a tunneling current that is rising like this up to this point. And then there is a negative resistance region. And then the conventional diode, the conventional PN junction diode. So the conventional PN junction diode follows the IV characteristic curves like this. So beyond this point, that is beyond this new voltage, it will follow the conventional tunneling diode. But interestingly, below the tunneling, below the new voltage, this tunnel diode can have a current across the PN junction due to quantum mechanical tunneling. Right. Now let's see what is called Schottky diode. So we know that a normal p-n junction diode is when you join a p-type semiconductor and n-type semiconductor, we form this p-n junction diode. Schottky diode is a diode formed when you are having a metal semiconductor junction. One of them is a metal here, and one of them is a semiconductor, let's say n-type semiconductor. The circuit symbol for Schottky diode is this. So there you see that please try to identify the Schottky diode from other diodes. So they will be slightly different, right? Now, so what will happen when you have a Schottky diode? Schottky diode means a diode in which there is a kind of what is called Schottky barrier. Okay, so when you have a metal semiconductor junction, just like we explained before, n-type has large quantity of free electrons in the depletion region, and those free electrons will diffuse to the metal, and the depletion region will be formed such that there will be a positive ions in the n-type semiconductor, and there will be a certain amount of negative ions in the metal side of the junction here. So the negative ions formed on the metal side of the junction for the junction in the on the metal side of this junction, as well as the positive ions formed on the semiconductor side of this junction, form what is called the Schottky depletion width. This is the depletion region. This is the depletion width. Okay, so here usually in the metal semiconductor junction, the depletion width is extended towards the semiconductor region, and since in a metal you have large quantity of free charge carriers already, the depletion width is usually very thin. Okay, the advantage here is the difference between normal p-n junction and the Schottky barrier Schottky junction is that in this Schottky junction, that is metal semiconductor junction, the depletion width is mostly within the semiconductor side. The depletion width on the metal side is extremely thin, always. Okay, so here in order to have electrical conduction across this metal semiconductor junction, you should be able to transfer the free electrons from the n side to the metal side. You should be able to transfer the free electrons from the n side to the metal side. Now, if the potential barrier that is developed across this metal and semiconductor junction is, if the barrier height is very large, then the electrons cannot easily overcome. Like if the barrier potential is if the barrier is very high, one thing you should know is that whatever line we are drawing is let's say the Fermi level. So the electrons in the metal side are below this Fermi level only, and the electrons cannot easily overcome this potential barrier. So this is called a rectifying barrier. Under forward bias means when you are connecting negative terminal of the battery to N side, positive terminal of the battery to metal side. This is called the forward biasing of a Schottky junction. So when you forward bias, you will be giving energy to these free electrons on the N side, and the electrons will overcome this potential barrier, and electrons will pass to the crossover to the metal side and will perform electrical conduction. That is forward bias. Now, when you reverse bias, that is when you put negative terminal of the battery to metal and positive terminal of the battery to the N side here. Under reverse biasing, electrons in the metal side of the junction is now supplied negative potential. So electron is supposed to travel to this side of the junction, but in order for electrons which are lying below the Fermi energy here to travel to the N side of the junction, the potential barrier height, if it is very large, if the barrier height, the potential barrier which is developed across this metal semiconductor, if this barrier height is very large, electrons cannot come to this metal cytojunction, therefore giving what is called a rectifying property. Rectifying property in the sense that it allows current to pass through this junction, metal semiconductor junction, only in one direction. Current is allowed to pass through only in one direction. But if in this case, if the barrier height is small, then in the reverse biasing, also in the forward biasing as well as in the reverse biasing, current can easily pass through this metal semiconductor junction. Such kind of junction is called ohmic junction or ohmic electrical contact. It will simply follow V equal to IR here. When the barrier height is very small, as you supply voltage, you will have a current, and the resistance across the PN junction will be V upon I. So in such kind of ohmic junction, the IV characteristics of this metal semiconductor will be something like linear, as good as linear. Okay, but in Schottky barrier diode, current will occur only. The current will pass through only in one direction of biasing, called the forward bias. So how that happens, we will just see. So this is a metal. So in a metal, you have what is called, you can assume a metal as a solids in which you have a large number of free electrons. So those free electrons will have a certain energy which is below the Fermi energy. So below this Fermi energy, you can assume that you have a pool of free electrons. And when you consider n-type semiconductor, we know that the Fermi energy of n-type semiconductor is lying close to the conduction band, and the Fermi energy of p-type semiconductor is lying close to the valence band. I don't know if I have discussed this. So yeah, we have talked about this when we talk about the donor level and acceptor level, right? So in n-type semiconductor, the Fermi energy is lying close to the conduction band. So when you are joining two solids here, the Fermi energy will align. There will be alignment of the Fermi energy. So Fermi energy of the metal, that is below this you have pool of free electrons, and this is the Fermi energy of this semiconductor n-type. So they will be aligned like this. So when you have such alignment of Fermi energy, what you call the vacuum level, the energy required to release the electrons from the metal surface, and the energy required to release the electrons from the semiconductor surface, the energy of those electrons which are released from such metal surface and semiconductor surface is called, the energy of such electron is called the vacuum level energy, E naught. Okay, so the work function for in the case of metal is you have to bring the electrons from this to the vacuum level, that is to release from the surface. And similarly in semiconductor, you have to supply enough energy with the energy such that the energy supplied is greater than the vacuum energy level E naught and EF difference. So this is the work function in the case of n-type semiconductor. But when you will join the two type of solids, that is n-type and n-type semiconductor and metal, this with the alignment of this Fermi energy, there will be a bending of this vacuum level. The vacuum level on this side is E naught here, and similarly it will result in a bending of what is called conduction band here, also result in a bending of what is called valence band here. And this is what you call a depletion region. This is the depletion region. So as I said, the depletion region is extending mostly towards the n-type semiconductor. On the metal, the depletion region is extremely thin, right? So this kind of band bending, valence band edge, conduction band edge, and this vacuum level bending will occur, and the Fermi energy will be aligned, right? So when you forward bias a Schottky diode, that is when you are connecting negative to the n-type and positive to the p-type here, electrons in this free electrons in this conduction band will be given enough energy to overcome this potential barrier, and the usual IV characteristics curve of this forward bias will more or less occur across this. But When you reverse bias, it is connecting negative potential to the metal and positive potential to the n-type. We know that when we study the depletion width under reverse biasing, the depletion width will increase. Under forward biasing, the depletion width decrease. So when the depletion width increases under reverse biasing, uh, you can assume that here electrons are lying here below this Fermi energy in the metal. So under reverse biasing, if the barrier potential here is quite high, that is, electrons cannot climb over to the if the electrons cannot climb over to this conduction band of this n-type. If the energy required for electrons to climb over to the conduction band of n-type is quite large, then when such barrier potential is quite large, you will have what is called a rectifying property. That is, under reverse bias, you will not have you will hardly have any current or the free electrons passing through this barrier potential. Okay, under reverse bias, the free electrons passing through this barrier potential is very less. So under such case, you have what is called this current is few microamperes. This current is few microamperes. So under reverse biasing, immediately after 0 volt, this is the 0 volt. Immediately after this 0 volt, the current in the reverse direction is like few microampere, and it will remain like that. So few microampere, you cannot record it in a normal conventional multimeter and all. So you can assume that there is no current passing through it under reverse bias. So therefore, showing what is called a rectifying property. It allows current only to pass through in the forward bias condition. Okay, and if you continue increasing the reverse voltage, this is the reverse voltage, this is the forward voltage. If you continue increasing the reverse voltage, then the breakdown of the junction will also occur like the usual conventional valence breakdown. So this is where the junction will burn. Otherwise, under reverse bias, no current is supposed to pass through this p and pass through this Schottky diode. Okay, so why are we so interested in a Schottky diode when we have a normal p-n junction diode which also has similar IV characteristics? The reason is that in Schottky diode, when you are forming metal semiconductor junction, the depletion width is extremely thin, because the depletion width on the metal side is only a very small, a very thin layer of ions at the surface of this junction. So when the depletion width is very thin, you can easily switch from the forward characteristics to